Welcome back. Let's talk about signed binary numbers. But before we do that, I want to show you this table from earlier in the notes in the first section just on number bases. There's this table right here. So in this table we have the binary patterns 0000 through 1111. So ignore the top row where I've added a fifth bit, but if you just look at these 4-bit patterns, we can count basically from 0 to positive 15, right, in decimal, from 0 to positive 15 with 4 bits. But what we need is a way to represent negative numbers, okay? So that is what we're talking about here with signed binary numbers. Okay, so there's many representations that have been tried over the history of computers, and one of the most recent ones is something called signed magnitude representation. Now, I'm only mentioning that so that you don't waste your time looking at it, because there is information out there on the internet about signed magnitude representation, and it will just confuse you, so it's more or less obsolete. What we've arrived on now is something called signed called signed 2's complement representation. So the theory for this comes from decimal, way back before computers, before binary computers. This was all figured out in base 10, or just regular decimal numbers. And it was interesting, but nobody really cared. But it turns out to be very useful for computers. That is the binary version of it, which is called 2's complement. And the reason it's useful for computer hardware is that it makes the hardware simpler. So let's say you want to add numbers. You need a circuit to do addition, so you have to have that. But if you wanted to do subtraction, you would need a whole nother circuit, and that's a fairly complicated circuit. So instead of that, they just have the addition circuit, and then they have a circuit that will flip all the bits. And flipping bits is a very easy thing to do in hardware. So once again, all you have is a bit flipper and the addition circuit, which you need to have anyway. So it makes the hardware almost half as big as it would otherwise be. So that's what's used in modern computers, is 2's complement. So let's look at how that's implemented in 4 bits. And real computers, of course, have I guess Windows and PCs are up to 64-bit integers now. But for a while, the first PCs were, I'm not sure if they made an 8-bit PC, but they had 16-bit PCs for a while, and then they went to 32-bit PCs, and now we're at 64-bit PCs. But we're just going to use 4 bits because that's enough for us to understand the theory. So what we do is, let's say we want to use 4 bits. We have to decide if we're going to represent those bits as negative, some of those bits as negative. And if we do that, then we assign values to all the bit patterns that are possible. So in this column here, we have all the bit patterns that are possible with 4 bits, and then we have the corresponding 2's complement numbers that are assigned to those bit patterns. So the way it works kind of is it starts at 0. If you start in the middle, you count up to 7. So all the positive numbers have a 0 in front of them, and we get like about halfway. We get up to 7. And then if you kept counting in positive, what would normally be positive 8 becomes negative 8, and what would normally be positive 9 becomes negative 7. This would be positive 10. Like that. And this column, if you interpret it as positive numbers, they keep counting up to the maximum. That's how I remember how to make the pattern. I start in the middle and I count up to 7, and then I go down here and I keep counting in binary up to 15, and then I fill in the positive and negative side on here. I mean, that's just how you would generate the table with 4 bits, or you could use that to generate a table of 5 bits or more bits than that. But the way to think of this really is that you have bit patterns, and then you have positive and negative values that are assigned to those bit patterns. That's the that's all we need to understand, really. The math theory behind this is, we don't need to really get into that much more than that. But you could try this with 5 bits or 6 bits, see how that works. All right, so if you're given, so here's the question. If you're given a bit pattern, how do you figure out what its value is? Let's say you're given a bit pattern and you're told that it's a 2's complement number, then how do you know what that decimal equivalent is? Well, if it's positive, that's easy. If it starts on the left with a 0, because all the positive numbers begin with a 0 on the left, then you know that it's positive, and then you just interpret it like you would any other binary number. So like this one, for example, that's just a 7 because it's a 4, a 2, and a 1. And this one right here is a 2 and a 1, so that's a 3. And they all begin with 0, so they're positive. Down in here, the patterns for the negative numbers are a little bit harder to interpret, so we need a way to interpret these negative bit patterns, the ones that start with a 1 on the left. So this is the pattern or the algorithm that's used. There's other algorithms, but this is what's done in hardware. We do this. We flip all the bits and then we add 1. Okay, so here's an example of interpreting a signed 2's complement number and getting its decimal equivalent. So you start with, let's say, what is the decimal value of 1001? So you start with that. You just flip all the bits. So 1 becomes 0, 0 becomes 1, 0 becomes 1, 1 becomes 0. You just flip all the bits and then add 1 to that, and then interpret the value or the pattern that you get just like you would on positive binary numbers. It's just add up the bits. 4, 2, and 1 means 7. And then remember that it's negative 7 because the original pattern we started with had a 1 in the front. Okay, that's basically it. So let's do it again. So what if you had a 1, 1, 1, 1? So you know that the leftmost bit is a 1, so that means this is going to be a negative value. So you do the flip and add 1. So you take all these 1s, you flip them to all 0s, you add 1, and then you add up the bits, and the answer is 1. Negative because we started with a negative value here. One more time. What if you were given 0, 1, 1, 1? Well, the leftmost bit is a 0, which indicates this is a positive number. So we don't have to do the flip and add 1. Right? We only do the flip and add 1 if the leftmost bit is negative, or leftmost bit is 1, indicating a negative value. So if it's 0, 1, 1, 1, we just interpret the bits by adding them up as we normally do. So 4, 2, and 1 means 7, and it's positive 7. All right? One more example. So the nice thing about this algorithm is it works with bigger bit patterns, and that's what's done in hardware with 64 bits. Or you could do it with even more bits than that if you wanted, if you needed to make your own integer that was bigger than 64 bits for some strange reason. But anyway, what is it with an 8-bit number? So take this 8-bit number. So it begins with a 1, so we know that the answer is going to be negative. So we have to do our flip and add 1 thing. So we start with our pattern. We flip all the bits, just reverse all the bits, right? Then add 1. And this 1 is going to carry on over. I didn't draw the carries here, right? This top row is not carries. This top row is the answer, or the example, the input. The problem we're trying to interpret, the bit pattern we're trying to interpret. So anyway, but if you added 1 to this second row here, the ones the carries would trickle over if you did that. And you'd end up with this. And then you just add up the bits. So this is the 128 bit. And once again, the answer is negative because of the original bit was 1 over here. All right? That's it. That's how you interpret a bit pattern that starts with a 1. That is, if you know that this bit pattern is a 2's complement number. It could have been an unsigned number. So there's signed and there's unsigned. And for unsigned, that's these guys. So the range here is 0 to 15. And if they're unsigned, or if they're signed rather, the range is -8 to 7. Right? It's the same patterns. So here in this table, these same patterns are used to represent positive numbers, and in this table, these same patterns are used to represent signed numbers. That is, some have a negative sign, or some the sign is negative, and some the sign is plus. Here, here over these we call these unsigned. They're all positive, but we call it unsigned, even though you could say that the sign is plus on all of these things. It's a little confusing on the terminology, but these are unsigned numbers. That is, they're all positive. And these are signed numbers. That is, some are positive and some are negative. So what we've just gone through is a way to interpret signed numbers. Really, the negative ones. How do you interpret the negative signed numbers? Because the positive ones was this example was a positive signed number, or also happens to be the same as the unsigned value. All right, you think about what I just said there. So we can go backwards. So let's say we have a decimal value. We want to find out what the 2's complement representation would be. So I'm using a -42. We want to turn that into signed 2's complement. So just reverse the algorithm. So subtract 1, do that first, and then reverse all the bits. So if you subtract 1 from 42, you get 41. And then in binary, positive 41 would be this pattern, because it'd be a 1, an 8, and a 6, and a 32. 32 plus 8 plus 1 gives you 41. So this is the pattern for 41, and then you flip all of those. So 1, 1, 0, 1 becomes, oh, sorry, I said that, I flipped them in my head there. So 0, 0, 1, 0 becomes 1, 1, 0, 1, and 1, 0, 0, 1 becomes 0, 1, 1, 0. All right? So I think I already, this section here is talking about the ranges of signed and unsigned numbers, and I think I already did that. But basically, you can see from the table, just real briefly again, if you look back at this table, if we have 4 bits, we can count from 0 to 15. So there's 16 numbers. 0 through 15 is 16 numbers. And the smallest one is 0 and the highest one is 15. And if we decide to use those 4 bits as signed 2's complement numbers, then there's still 16 numbers, okay, because there's 16 patterns that you can make, but the values are -8 to 7. And mathematically, or formula-wise, that's given by this right here. N is 2 to the n, the number of values big N can be represented using little n bits by this formula. Big N equals 2 to the little n. So, for 4 bits, 2 to the 4 is 16. So there's 16 patterns for 4 bits. And then the ranges 0 to 15 come out on this one, and then the -8 to 7 comes out on this formula here. So you can try that, and then here I've worked it out for, what would it be for 16 bits? And 2 to the 16 is 65,536. That's how many values. If you interpret those as unsigned, then it's going to be 0 to 65,537. Ooh, it should be 535. Typo. And if it were this one here, now I think this one's okay. I'll fix it in the notes and repost them. But I think this signed range is okay. All right. So back up a little bit. why do we have this stuff? Remember, the reason we have this stuff is because it's easier on the machine. That we only need an adder circuit and a complementer. We don't need a subtraction circuit. So let's try that and see how that works. So the hardware doesn't care. That's the thing to keep in mind. The hardware just sees some bits and it just adds them. It just throws them into the adder. So it just throws them into the adder. Like if it's doing addition, that's what it does. Now if it's doing subtraction, it would negate, it would invert one of the operands. Right? So if you're just doing A plus B, it would just send those into the adder. If you're trying to do A minus B, it would do A plus minus B. It would take the B and invert it. That is, it would flip all the bits and add 1 to get its negative value, and then it would just send it into the adder. So you only need an adder. Okay, so let's see what does that look like on some example problems. So let's pick a few. So it's helpful to have this table out here of 2's complement values so we can interpret them without too much work, just by looking them up in the table. So let's say we wanted to do -4 plus a -3. Remember, we're only doing addition in the circuit. It's just dealing with the 2's complement representations for these negative numbers. So -4, if you look in the table here, is 1100. Okay, and then -3, you look in the table, it's 1101. Then the adder circuit here, it just adds these this -4 and this -3. So this first 0 is a carry, so 0 plus 0 plus 1 is 1, carry the 0. 0 plus 0 plus 0 is 0, carry the 0. 0 plus 1 plus 1 is 0, carry the 1, right? Because 0 plus 1 plus 1 is binary 2, which is 1, 0. Right? Then 1 plus 1 plus 1 is 3, which is 1, carry the 1. And then you bring the last carry down. So is the answer any good? So it depends on whether you're interpreting the answer as signed or unsigned. So there's 2 bits that you look at. There's the signed overflow bit and there's the unsigned overflow bit. So this down here is the unsigned overflow bit, which is basically just telling you if the answer is too big to fit in 4 bits, which in this case it is. And then there's the signed overflow bit, which is generated by looking at these 2 bits, and it looks to see if these 2 bits are the same. So really the signed overflow bit is the result of XORing these 2 bits, because XOR will produce a 1 if both input bits are the same, right? XOR is this thing right here, right? You have XOR is it produces a 1 if both of the inputs are the same, if they're both 0, 0, or they're both 1. If they're both 0 or they're both 1. So that's why we call it the signed overflow bit, when really what you're doing is looking at these last 2 carries and checking if they're the same. Okay, so if they're the same, it means that the answer is a valid signed number, which this one it is, right? Because -4 plus -3 is -7, and that's what this is down here. If you look 1001, and you look in the table, that's -7. Okay, so if you interpret the answer as signed, you look at these 4 bits, and you can see from this table that it's telling you the answer is -7. And then you look at these 2 bits, and you see that they're the same, so it's telling you the answer is correct as a signed overflow. I mean, as a signed bit. As a signed. as a signed assigned number. It's correct as a signed number. But if you interpret this as an unsigned number, if you interpret the answer as an unsigned number, then this bit here, the unsigned overflow bit, is telling you that the answer is incorrect. Which it is, right? Because that's what I'm saying on the next page here. Where'd the next page go? Here's the next page. So if you interpret these two numbers that we're adding as unsigned numbers, then this is a 12 and this is a 13. And 12 plus 13 is 25, which is too big to fit in 4 bits. That's one way to think of it. Or you can think of it as, if you just look at the 4-bit answer, which is really where the answer is, it's just in these 4 bits. It's telling you that 12 plus 13 is 9, which is wrong, right? So that's, this bit here indicates that the 4-bit answer down here is incorrect if you interpret it as unsigned. Okay, so let me just kind of summarize what I just said. That the hardware doesn't care. It just takes this bit pattern and this bit pattern, adds them up, and gets this bit pattern, and that it just puts those out. And then it does. It puts out flags based on these bits here. It XORs these bits and puts out a flag called the assigned overflow bit, and then it takes this bit and puts it out as a flag indicating unsigned overflow. So, you know, that's what it does. It gives you an answer, and then it gives you some flags, and then it's up to the user, or in most cases some higher level software to generate an error. Okay, so once again, you know, it takes this bit pattern and this bit pattern and adds them together and gets an answer, and then it generates some flags, and then it's up to you, the user, or the higher level software to check if that answer is valid or not. In this case, if you're interpreting these as signed numbers, then the answer is correct. The answer is -7 because these two bits are the same. But if you're interpreting these 2-bit patterns here, or all of these bit patterns here, these 3-bit patterns, as unsigned numbers, then the answer is incorrect because it's trying to tell you that 12 plus 13 is 9, which it isn't. Okay, so you know that's how it works. Look at some more examples. So like let's try -4 plus a -5, and if y'all know remember from high school, that should be a -9. But -9 doesn't fit. If you look back at this signed 2's complement table, -9 is out of range for 4 bits. It doesn't fit, and that you can tell that it's the answer is wrong because these overflow bits here are different, indicating this answer is wrong. It's trying to tell you that this is a. It's trying to tell you that -4 plus a -5 is +7, which is incorrect. It's also incorrect if you interpret these as unsigned, right? It's unsigned is trying to tell you that it's just 12, 8, 9, 10, 11. 12 plus 11 is 7, which it isn't. So it's wrong. The answer down here is wrong using both interpretations. Okay, down in here, the answer down here is correct using both interpretations, right? Because +7 plus a -8 should be -1, and so that's what this is showing. This is +7. This is a -8 in 2's complement. -8. You add these up and you get 0, 1, 1, 1, 1, 1, which in the table here is -1, which is correct. 7 plus a -8 should be -1. So it's giving you the correct signed answer, and these signed overflow bits reflect that. These are the same. These two bits are the same, indicating that the signed interpretation of the answer is correct. And it also works for unsigned. So unsigned, this would be positive 7 plus 8 is 15, right? 1, 1, 1, 1 is 15. So that fits. 15 just barely fits. And the overflow bit is 0, indicating that the 15 is a valid unsigned interpretation. Okay, so it's, you know, a little confusing, but that's the way it works. And here's one more example, just using 8 bits. We're doing a -4 and -3, and I've got the I don't have an 8-bit table, but we could do the flip and add 1 on this 8-bit pattern to verify that it is indeed -4, and once we could also do the flip and add 1 on this pattern to verify that it is indeed a -3. And so -3 plus a -4 should be a -7. And this 8-bit pattern out here is a -7. If you did the flip and add 1, you'd see that it is. And these two bits are the same, indicating this value down here is correct. But if you interpret these two patterns as unsigned, they overflow. This pattern here would be 252, and this pattern here would be 253. You add those together, it's 505, which doesn't fit in 8 bits, right? The biggest 8-bit value is 255, right? So this 505 doesn't fit. So this is an invalid unsigned number, right? Which is indicated by the overflow bit being a 1. All right. Hope that made sense. So, you know, you can try working these manually, work some problems, which I've assigned in the first part of the next homework, I believe. And another thing you can do, if you feel like playing with it, is try this little C program right here. So a character in C is just an 8-bit integer. Okay, that's what it is. It's not, you know. So like if you do the default for a character is signed, so you don't have to put the word signed in front of character. If you leave it off, it'll be signed. And if you assign it a value 65, that happens to be the ASCII integer value for A, right? So you're basically making X, the variable X, contain the character A, if you want to think about it that way. But here we're just putting a 65 in it. So what's really in there? Well, I mean, I like to think of it as this is what's really in there, this binary pattern right here. You know, if you assign the decimal 65 to this signed value, that's what's in there, is 01000001. That's what's in there. Then what comes out on the display just depends on how you format that. So if you use these different format specifiers in printf, like this means integer, this means unsigned integer, this means hexadecimal representation, this means character, and then you're just outputting the same old X 4 times. I think here you have to have a type cast on here, I think, because I'm actually using C++. But anyway, what'll come out here is 65, I think, then 65 again, and then the character A. No, then the hex 41 will come out here on this one, and then the character A will come out on here. But if you do unsigned and assigned 136, you'll get 2 different values for the signed and unsigned, because 136 is out of range for unsigned, right? Unsigned or out of range for signed. Like the unsigned range is 0 to 255, but the signed range is minus 128 to 127. So this is too big, and it'll overflow. It'll interpret this when you do this. It'll interpret it as a negative number, and I think it'd be a good exercise for you to try this. See what you get. See what printf outputs on this, and then look at the bit pattern. Is this actually, what is this bit pattern if you interpret it as a it's a negative number? It should be the same as what you get over here. It's just something to play with, All right, so I think this should be. I hope this is enough for you to get the next section of homework done. I hope, fingers crossed. All right, I'll see you next time. We're going to talk about floats. All right, bye-bye.